Hello and welcome to today's lecture where we will talk about chemical energy storages, and here the storage itself and also the discharging technologies. About how to charge the storages, the chemical energy storage, we already have discussed the last time. Like always, you find the topic of chemical energy storage here in the book Energiespeicher Bedarf, Technologie und Integration that I have published together with my colleague Michael Sterne. And unfortunately it's still not available in English language, but it's already translated, and hopefully in the next months we will have it available in the bookshops. So to remember, the background was we have maybe in future excess electricity. With that we can generate gases, liquid and solid chemical energy carriers. And these energy carriers, then they need to be stored, and later they can be applied or discharged in different energy sectors. Chemical energy storage, apart from seasonal heat energy storages, chemical energy storage is the only nowadays known way to realize long-term energy storage. Even today, chemical energy carriers, coal, oil, gas, etc. are the backbone of our energy supply system. In renewable energy-based energy systems, they can be used as long-term storage and then be applied to different energy sectors. To the electricity sector, to the heating and coal sector, and the mobility sector. The storage facilities for chemical energy carriers, they are multiple. So we have those that are above ground, and there we know gasometers, telescope gas holders, spherical gas containers, gas pipe storages, floating roof tanks and many more. And then we have underground storages like porous storages, depleted gas and oil reserves, salt caverns, aquifer formations, rock caverns and abandoned mines, and again many more. Here are some photos. Here we see such a spherical gas container, or here we see an old gasometer. But those overground storages nowadays quite often are not anymore applied, as their storage volumes is not that big like what we need for our future energy supply. So quite often nowadays those old gasometers, today we for example have this one in Berlin that is used as a television studio, or this gasometer here in Duisburg nowadays is used as a diving pool. And the reason is that we want to have much more energy capacity, and that's the reason why we nowadays more go underground, like here in this salt cavern. How such a salt cavern is made? One drills a borehole until we come to a salt layer, and then just water is boiled in, and then the salty solution is taken out, and then of course this salty solution needs to process further, and when it's close to the seaside it can be brought to the sea, else another way it needs to be treated. But then we have those holes, those large holes, and then we can use them to store, for example, natural gas or renewably generated methane. Now we have a small video showing a bit this relation of sizes of above ground and underground storages. In order to illustrate how much space we have available in underground storages, we make a comparison here with this glass and the lake in behind. Here again a photo of a spherical gas storage. It has a diameter of 40 meters and a volume of 155,000 cubic meters of natural gas that already has been compressed to 10 bar. In all Germany we have a total storage capacity of 22 billion cubic meters underground storage, with different pressure levels ranging from 80 to 200 bar. That is significantly higher than a spherical gas storage. The volume of this glass should symbolize the volume of a spherical gas storage we just have seen. In comparison to that, the small lake in the background that has approximately then the storage volume of Germany's underground gas storage capacity. When all underground storages are charged, this is an energy equivalent of 200 terawatt hours. That is almost a third of Germany's electricity consumption per year. So the underground gas storages, they have a high safety according to unintended escape of gas. They are cheap in installation and operation, have a low land consumption above ground, have pressures or can realize pressures of up to 200 bar, and have high storage capacities. In average, a capacity is among 500,000 cubic meters. It is already state-of-the-art and has a high acceptance, the storage of hydrogen and methane generated by renewable power. Maybe a disadvantage is the requirement of pseudogeological formation. That is not everywhere possible, and the gas can be contaminated whenever what used before has been here in this underground storage. Here we see a good overview of all those underground storages. On the complete left side we see the porous storages and depleted oil reservoirs, and then more here on the right side we see salt caverns to store many things, among them hydrogen, methane or compressed air, for example. To sum that up, for storage of hydrogen and methane, for example, salt caverns are suited. They are technically tight, there's no contamination or pollution, they are suited for high charging and discharging power, they have a low investment operation and cost, but not to forget what we have discussed already before, the conversion technology to get hydrogen and methane, that is a quite expensive technology. On the negative side, we have that the extracted soil needs to be processed, and the salt caverns or other pseudogeological formations are not found everywhere in Europe. To get a number, the potential in Germany, there are a prognosis for the year 2050 that we will have almost 20 billion cubic meters in salt caverns and another 12 billion cubic meters in porous storages. And that's for the storage itself. And with the next video we continue then, after we already have dealt with to generate, to charge the chemical stores itself. So in the next video we continue with the technologies for discharging the chemical energy storage. So thank you very much for your attention.